The sun has provided light to Earth for billions of years. It can both sustain and destroy life. While some creatures thrive in its warmth, others are incinerated by its heat. Despite its proximity and millennia of observation, the sun remains a largely mysterious entity. Studying it is challenging and requires painstaking effort. Hello and welcome to Z. Please don't forget to subscribe and hit the bell icon. How well do we really understand our closest star? Let's find out. Cosmo, the first in outer space. On November 21st, 2021, the Parker Solar Probe came within 8.5 million kilometers of the Sun, its closest approach ever. This marked the first time a probe touched the Sun's corona, the extremely hot outer layer. But why undertake the technical challenges to get so close? What information does Parker seek that required such a perilous journey? To understand this, we need to revisit our knowledge of the Sun. It is a main sequence star about 4.6 billion years old, classified as a G2V yellow dwarf. Its surface temperature is around 5,800 Kelvin, 5,530 degrees Celsius, with both hotter and cooler regions. The Sun's inner layers and corona reach millions of degrees, contributing little to visible light. With an average diameter of 1.4 million kilometers, 109 times that of Earth, it is massive, weighing 2 times 10 to the power of 30 kilograms, or 333,000 times more than Earth, comprising 99.9% of the solar system's mass. Although the Sun appears small, it is larger and brighter than 80% of the stars in our galaxy. Hydrogen constitutes 92% of its volume. In a previous video on stellar evolution, we discussed how thermonuclear reactions in stars transform hydrogen into helium, releasing immense energy. Currently, helium makes up 7% of the Sun's volume and 25% of its mass, with trace amounts of other elements like carbon, oxygen, nitrogen, and iron. The Sun's complex structure includes several layers with different properties. At its center is a massive core, about 25% of the Sun's size, with a temperature of 14 million Kelvin and a density of 150 tons per cubic meter. This is where thermonuclear reactions power the Sun's light, converting approximately 4.26 million tons of stellar matter into energy each second. Surrounding the core is the radiation zone, extending to 70% of the Sun's radius. Energy here is transferred through photons continuously absorbed and re-emitted by stellar plasma particles. The temperature in this zone ranges from 7 million Kelvin at its base to 2 million Kelvin at the outer edge. Light produced in the core can remain in this zone for 10,000 to 170,000 years before moving outward. Above the radiation zone is the convection zone, the Sun's outermost layer, where less dense and more turbulent stellar matter forms enormous vortices. These vortices transport hot plasma to the surface, while cooler plasma descends. This movement creates a magnetic field that extends throughout the solar system. The Sun's atmosphere consists of several layers. The photosphere, emitting most visible light, is 100 to 400 kilometers thick, with temperatures between 6,600 and 4,000 Kelvin, 6,330 to 4,130 degrees Celsius. Above it lies the chromosphere, a 2,000-kilometer thick layer observable during a solar eclipse or with special equipment, with temperatures ranging from 4,000 to 20,000 Kelvin. Its outer border is covered with spicules, jets of hot gas rising up to 10,000 kilometers. The corona, the Sun's outermost atmosphere, features giant prominences, flares, and emissions up to 1 million kilometers in size. Despite its rarity, it is extremely hot, with temperatures averaging 1 to 2 million Kelvin and peaks at 20 million Kelvin. The Parker probe frequently traverses this blazing region, delving deeper each time. The energy flow from the photosphere is insufficient to heat the chromosphere and corona to their high temperatures, suggesting unknown physical phenomena. Hypotheses propose additional energy might come from dispersing magnetic shock waves or the acceleration of charged particles in the Sun's magnetic field. The Parker Solar Probe was designed to investigate these mysteries and study processes in the Sun's upper atmosphere. Launched in 2018 as part of NASA's project, the Parker Solar Probe used Venus's gravity to adjust its trajectory, approaching the Sun. Equipped with a heat shield and designed for extreme conditions, its orbit allows brief close encounters with the sun before pulling back to cool down, mitigating thermal stress. Parker's primary goals are to map magnetic fields near the sun, measure energy flow, capture stellar wind particles, and observe wave-like processes in the corona. It also took photos of Venus and comet Neowise. The probe carries various scientific instruments, including cameras, particle detectors, magnetometers, and radiation sensors. Despite facing critical temperatures and ionizing radiation, Parker continues its mission, getting closer to the sun with each orbit. By February 2022, it passed through the corona again to gather more data. By 2024, it will approach within 6.5 million kilometers of the sun, with its solar shield heating to 1370 degrees Celsius. Traveling at 163 kilometers per second during its closest approach, Parker will eventually accelerate to 200 kilometers per second, becoming the fastest man-made object. Its mission will last about a year, during which it will orbit the sun, lose speed, and face extreme conditions until it ultimately succumbs to the sun's heat and radiation. Before its end, Parker will transmit valuable data back to Earth, advancing our understanding of space and proving its mission was worthwhile. The Parker Solar Probe, launched by NASA in 2018, represents a groundbreaking mission aimed at unlocking the mysteries of the sun by venturing closer to it than any previous spacecraft. Named after solar astrophysicist Eugene Parker, the probe's discoveries have significantly enhanced our understanding of the sun's structure, behavior, and its profound influence on the solar system. Discovering the solar wind's origin. One of the primary objectives of the Parker Solar Probe was to study the solar wind, a stream of charged particles that emanates from the sun and permeates the entire solar system. The probe has provided unprecedented insights into the solar wind's origins and its acceleration mechanisms. It revealed that the solar wind is not a uniform flow, but consists of discrete, dynamic structures known as switchbacks. These sudden reversals in the magnetic field direction were previously unknown and suggest that the solar wind is more turbulent and complex than previously thought. Understanding these switchbacks is crucial for comprehending how the solar wind transports energy and particles across the solar system. Unveiling the sun's magnetic field. The Parker Solar Probe's close approach to the sun has allowed scientists to examine the solar magnetic field in unparalleled detail. The probe's instruments detected magnetic structures that were previously undetectable from Earth or other spacecraft. These observations have shed light on how the sun's magnetic field is generated and how it influences solar activity, such as solar flares and coronal mass ejections, CMEs. By studying these phenomena, scientists can better predict space weather events that can impact satellite operations, communication systems, and power grids on Earth. Exploring the corona's mysterious heating. The solar corona, the sun's outer atmosphere, is millions of degrees hotter than the surface of the sun, a phenomenon that has puzzled scientists for decades. The Parker Solar Probe's measurements have provided new clues about this enigmatic heating process. The probe detected high-energy particles and waves in the corona that may be responsible for its intense heat. These findings support the theory that magnetic reconnection, a process where magnetic field lines break and reconnect, releases vast amounts of energy and heats the corona. Understanding this process is critical for explaining the sun's behavior and its impact on the solar system. The Parker Solar Probe has also made significant contributions to our understanding of how solar energetic particles, SEPs, are accelerated. These particles, which can travel at nearly the speed of light, pose a hazard to astronauts and spacecraft. By directly sampling SEPs in the vicinity of the sun, the probe has identified the mechanisms responsible for their acceleration. It discovered that shock waves generated by solar flares and CMEs play a key role in propelling these particles to high velocities. This knowledge is essential for developing strategies to protect space missions and astronauts from the harmful effects of SEPs. Observations of dust-free zones. Another intriguing discovery made by the Parker Solar Probe is the identification of dust-free zones near the sun. As the probe approached the sun, it observed a region where the density of interplanetary dust particles significantly decreased. This finding suggests that the intense radiation and solar wind near the sun are capable of vaporizing dust particles. Understanding the distribution of dust in the inner solar system is important for comprehending how the solar wind interacts with other cosmic materials and influences the formation and evolution of planetary systems. The Parker Solar Probe's discoveries have revolutionized our understanding of the sun and its complex interactions with the solar system. By venturing closer to the sun than any previous mission, the probe has provided invaluable data on the solar wind's origin, the sun's magnetic field, the mysterious heating of the corona, the acceleration of solar energetic particles, and the existence of dust-free zones.